Professor Rad here, and today we're going to talk about an introduction to conic sections. Now, in this video, we're basically doing a terminology dump. We're going to learn a whole bunch of vocabulary and look at some variables that are used to represent certain values. We're not going to work through any examples in this video. We'll be working through those in the next one. But the purpose of this video is to introduce you to that terminology and to create essentially a reference sheet that you can refer back to as you work through those examples. So when we talk about conic sections in pre-calculus, basically what we're doing is we're getting a little sneak peek into a field of math called analytical geometry. So far this semester, we've been looking at things very algebraically. So we look at an algebraic expression, and then from that, we develop a graph. That's pretty much our approach to things. In analytical geometry, it's a very different approach, a very different feeling to math. So we'll see that when we examine parabolas, because we're used to how we've thought about parabolas so far, and now we're going to think about those same objects, but in a very different way. So in analytical geometry, you take a geometric object and then you analyze it. And then from there, from that analysis, you get things like the algebraic expressions. So in this case, conic sections are sections of a cone. Pretty boring explanation there, but let's see what that means. So first, what is a cone in math? So in math, a cone is created by taking a stick and rotating it about a fixed point. So for example, if I look at this image of a cone here, where the two, what we would colloquially call cones meet, that would be our fixed point. And envision this as like the stick, and then you rotate the stick around, and that's creating this what looks like a double cone. So colloquially, we would think of this as like two ice cream cones glued together, but really an ice cream cone is only half a cone. It's not the full thing. I wouldn't recommend putting ice cream into the bottom of a cone though, because then it would just all fall out, and that's no fun. So to create a conic section, what you do is you slice the cone up in different ways and you get these different kinds of shapes. So for example, if I slice the cone parallel to the stick that I rotated, I end up getting a parabola. It's pretty cool that that happens. So we can see if I trace along this edge of that cone and then along the back edge of the cone, that's how we're getting our parabola. If I slice it parallel, I guess, to the opening of the cones, then I end up getting a circle, right? And if you think about looking at like an ice cream cone, the top of it is a circle, so that makes sense. And if I slice it sideways, then I'm not going to get a perfect circle. I'm going to get kind of a slanty circle, which we'll call an ellipse. Okay, so this isn't going to be perfectly round. It's going to be a little bit squashed in one dimension. And then lastly, if we slice the cone up and down, but not parallel to the stick, right? So the parabola, we were parallel to the stick, but if I switch that angle, you can see if I were to draw a line, I would hit the cone in both the top and bottom pieces. So that's what's going on here. I'm hitting the cone in both the top and bottom pieces, and that's creating the hyperbola. So because I'm hitting both top and bottom, a hyperbola has two separate pieces. It's got that bottom piece and the top piece. So this is the different types of our conic sections. Now let's take a look at each of these three in a little bit more detail. Okay, so let's start out with a parabola. So the definition of a parabola is the set of all points that is the same distance from a particular line as it is from a particular point. So in this case, the directrix is this blue line. The directrix is the line. And then the focus is the point. So the focus and the directrix aren't on the parabola, but they're used to generate or create the parabola. And everything that's on this black line, that's our parabola, is the same distance from the focus as it is from the directrix. So for example, if I look at this pink line here, that's our vertex of our parabola, right? That's the turning point of the parabola. If I look at the distance from the pink point to the directrix, that's the same as the distance from the vertex to the focus. Or if I pick a random point, let's say this point here that's on the parabola, This distance to the blue line is the same as the distance to the purple X. Okay. So everything is the same, it's equidistant between the line and the focus. Now you'll notice there's a green line here. This is called the lattice rectum. This is the line that goes through the focus and is parallel to the directrix, rather the line segment. Let's see, this distance here is going to be twice the distance as this one here. So here's why that happens. So first, let's define this distance. This distance we're going to call A. It's the shortest distance between a point and the focus. So we can see A is the distance from the vertex to the focus. And for the focus is a distance of 2A from the directrix. And if I go 2A up, that gets me to the edge, because now I'm 2A away from the focus and I'm 2A away from the directrix. Okay. So those 2 points, there's one on top in this case and on bottom, that's going to give us our lattice rectum. So let's deal with numbers here, right? So in this case, A would be 2 because the focus is 2 away from the vertex. So 2 times 2 is 4. And if I look at this distance here, it should be 4. So we've got 1, 2, 3, 4. And then if I count from here to the directrix, it's also 1, 2, 3, 4 away. So that's our 2A happening, and this is A happening. And then the last part of this image is the axis of symmetry, and that is, as we always know it to be, that's the line through the center of our parabola, so it's perpendicular to the directrix or the lattice rectum. And if we fold the parabola about it, it matches up perfectly. So those are all the terms. The one thing I didn't mention are the coordinates of the vertex, that's HK, just like we use for, in the old times when we looked at a parabola more algebraically, we had its vertex was HK, so we're going to continue with that notation for here. So you'll also notice this parabola is different from ones we looked at in the past because it is sideways. So we're actually going to look at parabolas that are sideways this way, or kind of if I flipped it, if it opened the other direction, as well as parabolas that open up or down. So we're going to look at those formulas for those. It's going to look a little intimidating, but hopefully I can break it down a little bit for you. So when we're dealing with conic sections, it's going to be really important to remember a few things. For example, the pieces that you're playing with are usually going to be like an x minus h and a y minus k. And then we'll have letters. In this case, we only have A, but in the future, we'll also have B and C. So x minus h, y minus k, A, B, and C. Those are going to be your pieces that you're moving around. The shape of a parabola's formula is going to be something squared equals plus or minus 4a something. So if I look at each of these formulas, we have something being squared. So in each of these, we have something being squared equals, and then it's either a positive or negative 4a. So here we have a positive, here we have a negative, positive or negative, times something. So here we have, again, either an x minus h or a y minus k for that something piece that we get multiplied by. So for a parabola, we have something squared equals plus or minus 4a times something. Now here's how you determine what each of those somethings are. So if it's a normal looking parabola, so for us, that means it's opening up or down, right? Those are the parabolas we're used to. Then the something squared is the part with the x. Because if we think of our usual parabola formulas, it's always got an x squared in it. So the something squared is the x minus h. If it's a sideways parabola, the something squared is the y. So we have y minus k being squared. And then whichever one's not being squared is the other thing. So since here I have an x minus h being squared, then y minus k is the other something. On this one, y minus k is being squared, so x minus h is the other something. And then lastly, whichever axis is being eaten tells you whether the 4a is positive or negative. So for example, this parabola if I think of it as a mouth, it's eating chomp, 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 a positive x-axis or parallel to the positive x-axis. So we have a positive 4a. Whereas this parabola down here is chomp, 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 eating a negative x-axis or parallel to the negative x-axis, that side. So we end up with a negative 4a. So left and down are negative, up and right are positive, just like our axes. So whichever one you're eating, that tells you whether 4a is positive or negative. So again, just to reiterate, the shape, something squared, equals either a positive or a negative 4a times something. If it's a normal parabola up or down, then it's the x thing that's being squared. If it's sideways, it's the y thing being squared. And then whichever direction of an axis it's eating, then that's going to tell you the sign of the 4a. Now, the rest of this stuff, F is for focus, D for directrix, AOS is our axis of symmetry, and LR is our lattice rectum. These formulas you can do with as you will. Me, personally, I have trouble memorizing information, so I don't memorize those formulas. I recreate them from the graph. So for example, if I have an equation of a parabola, then I'm going to go ahead and graph it. And then to figure out the coordinates of the focus, then I will move over that amount. Or if I have a vertex and a focus and I need to figure out where the directrix is, I will graph the vertex and the focus. I'll figure out, okay, here's A is 2. And so the focus and the directrix are on either side of the vertex. The vertex is in the middle. So that will tell me the directrix needs to be over here. So for instance, if I had the same vertex, but the focus was up top, that would tell me the directrix is the same distance below. So in that case, the directrix would be a horizontal line. So like I said, that's how I remember, that's how I work through finding a focus, directrix, axis of symmetry, or lattice rectum. If you want to remember these equations associated with this, each of the formulas, you can feel free to do so. But that's just not how my brain works. So whatever works best for your brain, go with that. So now let's take a look at the second type of conic section, which is our ellipse. So whereas a parabola is generated by using a point and a line, an ellipse is generated by using two fixed points. And the way that I think of an ellipse being created is I tie a string to each of those two fixed points. So here our foci are once again going to be our fixed points. So one end of the string gets tied here and one end of the string gets tied here. And the string is loose, so just imagine it's dangling here, right? So then what I do is I pull that string tight and I trace the circle or the shape that amount results from it. It's not a circle, it's an ellipse. So if I imagine my string is now tight, right? So here's my string. As I move it around in a circle, I keep the string tight, but it creates this ellipse. So that's how the ellipse is created. Now for the pieces of the ellipse, the center is halfway between the two foci. And that kind of makes sense. It's in the center of our ellipse. And with your ellipse, because it's kind of like a squashed circle, it's going to have one axis that's larger than another. So the larger axis is the one that runs through the foci, and we call that the major axis. And where the major axis intersects the ellipse, we call those the vertices. So this is a little bit weird because, like on a parabola, a vertex is a turning point. It's kind of strange to think about that for a roundish shape, but that's what the vertices are here. And then the shorter axis is called the minor axis. So those are the components or the pieces of our ellipse. Now let's go for the letters that we're going to use to represent various distances. So first, HK, instead of being a reference to a vertex, HK is now our reference to the center. So think of this kind of like when you think of a circle. For a circle, HK is your center and R is your radius. So we want those kinds of components for the ellipse. So HK is going to be the coordinates of our center. A is going to be the distance from the center to the vertex. Okay, so if you wanted to, you could think of that like the larger radius, if you will. Okay, so that's A. And then B is like the shorter radius. I'm using these words colloquial here, colloquially, not specifically mathematically, but it's this shorter distance here is B. And then C is this distance from the focus to the center. So if I look at those three distances, A, B, and C, the longest distance is going to be A because that's along the longest axis and it goes from the center to the end. So we have a relationship, which I'm not going to establish or prove here, but we get this relationship similar to, but different from the Pythagorean theorem, that A squared is B squared plus C squared. In other words, A squared, this longer distance, is the same as the shorter distance squared plus this shorter distance squared. So that's a relationship that we'll need to know if you know, for example, B and C, but you don't know A, or if you know A and C, but you don't know B, right? So this relationship between A, B, and C is going to be important. So here are the two formulas for an ellipse. We're going to look at horizontally ellipse and vertical ellipse. And the way that I remember these formulas is very similar to the parabola way that I remember them. So I think about the shape of the equation and then the components in the equation. So just like with the parabola, we have x minus h, y minus k, and this time we have an a and a b in the formula. Notice that c does not make an appearance in the formula. The formula for an ellipse is really similar to a circle, but what's different, in a circle, you would just have this x minus h squared plus y minus k squared equals r squared, because you have a constant radius all the way around that shape. But for an ellipse, as we saw, that radius isn't constant, it changes. So here, what we're going to do is we're going to have it equal to 1, and the a and the b are kind of like scaling factors for those radii. So the way that I remember it is it's like a circle. So it's something squared plus something squared equals 1. And then the part that gets associated with a squared is the longer axis that you're associated with. So for example, this one is squashed horizontally. So the x piece gets the a squared, and the y piece gets the smaller, gets the b squared. This ellipse is stretched vertically, so its major axis would be parallel to the y-axis. So now the y stuff has the a squared, and the x stuff has the b squared. So the shape for an ellipse formula is something squared plus something squared is 1. Whichever axis is stretched longer, that's what gets associated with the a squared. And then the other one gets associated with the b squared. Then, as before, with the foci, the vertices, and the major and minor axes, I use the graph to help me figure that out. So I map out all of the different pieces and kind of move from there to figure out those components. And again, this formula helps me figure out C. However, if you wanted to, you could memorize these formulas with their associated, big equation of the shape up here or the general picture of it there. And lastly, we have the hyperbola. So this picture looks a little bit like a mess. So let's take a moment to be overwhelmed by it. Okay, and let's walk through it. So the way that I think of an ellipse is kind of like you're enclosing the foci, and they're together inside the shape. And with a hyperbola, it's sort of exploded outwards, like an ellipse, but exploded outwards. So notice that the foci on this graph are not between the two black lines, they're kind of on the outside of them. So this hyperbola opens vertically, and the foci are on the outside of the graph, whereas the vertices are in the inside. Okay, that's the opposite of what was going on with an ellipse. The way a hyperbola is created is instead of the sum of the distances between the two foci being the same, that was an ellipse, now we need the difference of the distances between the two foci to be the same. When you create a hyperbola, you have a whole bunch of axes going on here. We also have our center, so let's point that out first. So we've got the center, which is halfway between the two foci, and then we have our vertices, which are in between the foci, on the inside this time. For our axes, our hyperbola is eating the transverse axis. So if I think of this as like a mouth and it's jumping up, it's eating the vertical axis here. And then the conjugate axis is kind of in the no man's land. So the conjugate axis is in between, halfway between the two components of our hyperbola. And then lastly, we have two asymptotes. They have the same slope, but opposite signs. So we have one asymptote here, and then the other asymptote here. And this one you can kind of think of as like the clearest indicator that this is a piece of a cone. If you think of these asymptotes kind of as like the limits of the cone's sides, and then our hyperbola is fitting within there. So that's kind of how I like to think of it, kind of, you know, my own little way. So as with an ellipse, we have an A, B, and C, and this time it is similar to the Pythagorean theorem. So we have a squared plus b squared equals c squared, which means instead of A being the longest distance, our longest distance is now C. And I should point out, HK is our center as usual. So let's see what A, B, and C are this time. So as with the ellipse, A is the distance from the center to the vertex, and C is the distance from the center to the focus. So that's the same as it was on the ellipse. A is the distance from the center to the vertex, and C is from the center to the focus. Cool. B is a little bit harder to explain, as you can kind of see here. So B comes from the slope of the asymptotes. So if I think of the asymptote that's going on here, one way to find the slope would be, in this case, go from the center up to the vertex and then go over to the asymptote, right? So this would be my rise, and then here I have my run. On this hyperbola, the run is B. Now I'm saying on this parabola, or hyperbola, sorry, because we'll see if the hyperbola is opening sideways, the rise and run are flipped. We'll get to that in a minute. But on this picture, right, the rise is A, because it's the distance from the center to the vertex, and then the run, if I go perpendicular to the transverse axis, that tells me B. So you get B by knowing the slopes of the asymptotes and the vertices, and that A, sorry. All right, so let's go ahead and look at the formulas for these things. So we're going to have two kinds of hyperbolas. This one down here looks like the one we were just looking at, and this one here is sideways. So again, with the shape of the equation for these objects, it looks very similar to the ellipse. The difference is we have subtraction instead of addition, and that's because you can think of it anyway, because the distance of between the 2 points, the difference of the distances between the two foci has to be consistent. So since it's a difference in its definition, we get a difference in the definition in the equation. So there's connection there. Again, we have our pieces x minus h, y minus k. And what's different is that order is important since we're subtracting now. So if my hyperbola is eating the x-axis, so this one's eating the positive and the negative x-axis, then the x comes first and it's associated with A. If it's a vertical hyperbola, so it's eating the y-axis, then the y comes first and the y is associated with A. So still, whoever's associated with A is the one that you're eating, you're chomping, but this time it has to come first. And then the other one gets associated with the B. What I was mentioning with the rise and the run is showing up here in our equations for our asymptotes. So we can see that for a vertical hyperbola, like we were just looking at, the rise was A, so we went up and then over for B. But if I'm one of these kinds of hyperbolas, to go from the center to my vertex, I'm going over, so that's my run. So B would be the rise, and then A would be the run. So here we have our rise is B, and A is the run. So you still find it the same way. You still find it by, you still find B by using the slope of the asymptote. However, you want to be careful based on whichever axis comes first, flips what that slope looks like in this formula. So again, you can memorize that with these formulae, or you can sketch out components of the graph and work from there. So in the next few videos, we'll work through some examples of doing that, hopefully to make these formulas make a little bit more sense. But I did want to kind of lay down all the terminology and get through the formulas before we work through an example, so we have everything in one nice reference sheet. So yeah, so hopefully this helped you at least know what the pieces are, and then in the next few videos, we'll start putting them into context. So looking forward to seeing you then. In the meantime, I hope you have a wonderful day.